Unmute. Now, okay. So now hopefully people can hear. Okay.
A good chance for the and there is nice because a lot of people in the training the offshore from other states. They are very interested, but they so. Bom dia, pessoal. Temos o prazer de receber aqui o Dr. Emilio Martinez-Pañeda, com Inaugural de Londres. Dr. Emilio Martinez-Pañeda is an associate professor in mechanics of material at Imperial College, where he leads the mechanics of infrastructure materials lab. Prior to joining Imperial College, Dr. Martinez-Pañeda was the 8th Research Fellow at the University of Cambridge. His research interests span a wide range of topics with applied mechanics, such as corrosion, battery degradation, material plasticity, among other things. Dr. Martinez-Pañeda has published more than 80 scientific papers in the best journal in the field, and received numerous prestigious awards and fellowships for his contributions. Among others, Dr. Martinez-Pañeda is the recipient of the Imperial Medal for Excellence in Research, Williams Gustavo Paulani Medal, IMEX Prestige Award for Risk Reduction Mechanical Engineering, and the Royal Academy of Engineering UK's Younger Engineer of the Year. So thank you very much for being here. It's our pleasure to have you here in the inaugural lecture of the project.
Obrigado, Fernando. Yeah. Thank you very much, Fernando, for your very kind introduction and invitation, and thank you all for coming. I'm really delighted to be here. So as Fernando said, my name is Emilio Martinez-Pañeda, and I am an associate professor at Imperial College London working in the area of mechanics materials. However, as you can probably guess from my name, I'm not British. I was born and raised in Spain, in a region called Asturias, which is located here in the north of the country, northwest of the country. And it's a very beautiful region, as you can see here. Not as beautiful as Rio, but quite beautiful anyway. We have lots of beaches and mountains and cows and cathedrals, so it's quite a nice place, and I'll certainly recommend all of you to visit. However, it's been a long time since I don't live in this nice area of Spain. My academic career has taken me all over the world. I did start first doing my undergraduate degree at my home university, the University of Oviedo. This is normally what we do in Spain. But then my PhD and my subsequent academic career have taken me all around the world. First to Denmark, to the Technical University of Denmark in Copenhagen, and then to the University of Cambridge, where I arrived in. I did part of my PhD in Cambridge, but I arrived permanently to the UK in September 2017. So it's been a while now. From the University of Cambridge, then I moved to Imperial, which is a very great place to be. I feel very privileged to be able to work at Imperial. It's a very dynamic institution with lots of talented people from all over the world. And it's also very nicely located, so there's multiple campuses, but the main one where I'm sitting is in the South Kensington campus, which is what you see here. And what you see in the north here is Hyde Park, so it's very well located within London, and this is the Natural History Museum, so it is in this very touristic area of London. I think if somebody has been to London as a tourist, you will probably recognize this area. And of course, you're all most welcome to visit and to drop, feel free to drop me an email if you're around. I'll be happy to show you Imperial. My office is somewhere here near this tower. And at Imperial, I established my research group, which is the Mechanics of Infrastructure Materials Lab. There's one Brazilian, by the way, Livia here. And I think I should emphasize that I've been very fortunate to attract to my group very talented individuals. And it's really a great pleasure to work with them. And what these talented people do is to tackle scientific challenges at the interface between mechanics and other disciplines, such as chemistry, material science, geology, biology, or computer science. We both use experiments and modeling, and we typically try to adopt a multidisciplinary approach, combining mechanics with other physical phenomena. And we work on a wide variety of mechanics problems, all the way from large-scale problems such as ice sheet fracture or iceberg calving to improve sea level rise projections, all the way to the behavior of small chips and science effects in plasticity that are associated with the mechanical behavior of these devices. But today I'm going to focus on three problems that I like, that I particularly like, and that I think are particularly relevant because they're related also to the energy transition. So they're both scientifically challenging and stimulating, but at the same time relevant to engineering practice and society. So these are the three problems that I'll be talking about in this order. I will start by talking about hydrogen embrittlement, how hydrogen interacts with metals. Then I will move on to lithium-ion battery degradation, and then finally we'll talk about localized corrosion and corrosion damage. And I should say that I'm working on these three problems, both using experiments and modeling. But today, for the sake of time, I'm going to focus on the modeling part of the work. And yeah, as I said, let me start with this hydrogen. But before I start, I should say there's one tool that we use quite significantly in all these problems. So there's one tool that has basically opened new modeling horizons for us in all these three problems. So I'm going to say a few words about it. This is what we call phase field modeling. And the idea is quite simple. So whenever you have an interface, or whenever you have two phases, you can describe the interface as either sharp and discontinuous, or instead you can smear that interface over a finite domain using an auxiliary variable, the phase field, and then track the evolution of and basically this phase field will take two distinct values in each of the phases. So it can be 0 in the blue phase, 1 in the red phase, and then it will vary smoothly between. And then you just need to solve a differential equation for the phase field, and you're able to track the evolution of interfacial problems of arbitrary complexity. So this could be cracks propagating, this could be great boundaries evolving, whatever interfacial problem that you have, this very simple computational idea is quite powerful, and it allows you to track easily interfaces. And there's three key advantages that I always like to emphasize. The first one is that the interface equation is defined in the entire domain, so there's no need for any special treatment. The second one is that topological changes such as merging or divisions of interfaces can be naturally captured without any ad hoc criteria. And the final one is that it's very well suited for multi-physics problems, because you can easily couple that interface equation with equations describing other physical phenomena. So this is something that we're going to use quite significantly. And in fact, phase field modeling has revolutionized many areas of science and engineering. Everything started in the condensed matter physics community and is now by far the most popular tool to simulate microstructural evolution and solidification. It has also very quickly become popular in the fracture mechanics community. I think I read that roughly a third of fracture mechanics papers these days are using this methodology. And we have also very recently shown that it could also be used to describe the evolution of the corrosion front. And these are all simulations, by the way. You can see very complex interfacial phenomena can be captured. If you look at the fracture problem, you can see that you get crack branching, coalescence of multiple cracks, initiations of cracks from secondary sides. Or here you can see in corrosion how you can predict material dissolution, the evolution of the corrosion front, across secondary particles, and so on and so forth. So it could potentially be a very compelling tool. And I was going to use this for many of the problems that I'll be discussing later on. So let me go back to the content of my talk. And just to motivate this, I think a big part of the motivation to work on hydrogen these days comes from the energy transition. We know that hydrogen is typically called the Swiss knife for decarbonization, and we know that it's going to play a key role in this energy transition. And this is because hydrogen has the potential to decarbonize many applications and sectors, including some that are going to be particularly difficult to decarbonize, such as steel making or aviation. And I think the key thing to me is that this needs to happen very fast. For example, Airbus is saying that they will have hydrogen fuel airplanes in the air by 2050. The European Union is saying that they were going to 2035 actually, not 2050, 2035 they're hoping to have hydrogen fuel airplanes. The European Union is hoping to deploy over the next 15 years 40,000 kilometers of hydrogen transport pipelines. So things need to happen very fast. And there's an urgent need to deploy a hydrogen energy infrastructure that currently doesn't exist. But the problem with hydrogen is that it has a dark side. We know since almost 150 years ago that hydrogen makes metals very brittle. You can see here, this was a paper by Johnson in the Proceedings of the Royal Society back in 1875, where he speaks about some remarkable and extraordinary decrease in toughness and breaking strain in iron and steel in the presence of hydrogen. And in those days, it was very rare to see words such as remarkable or extraordinary in scientific papers. But the way hydrogen interacts with metals is indeed remarkable and extraordinary. So one of the things that we observed is a very significant reduction in ductility with increasing hydrogen content. You can see this here. These are uniaxial stress strain curves. And you can see that if I introduce hydrogen into my samples, I get a very significant reduction in the failure strength. Another thing that we observed is a reduction in fracture toughness. You can see here that we go from a fracture toughness of 150 megapascal square meter to well below 40 megapascal square meter if I introduce hydrogen into my samples, for example, by exposing them to hydrogen gas. And this degradation in toughness also carries an acceleration of fatigue crack growth rates. So here you're showing fatigue crack growth rates without hydrogen and with hydrogen. And you can see this is a log scale. Hydrogen increases by orders of magnitude the crack speed in under fatigue loading conditions. And all the results I've shown so far are for mid-strength steels. But in high-strength steels, this susceptibility to hydrogen damage increases dramatically. So you can get fracture reductions, fracture resistant reductions of orders of magnitude in these high-strength steels. And this is a key point to emphasize. The susceptibility to hydrogen damage increases with the material strength. You can see here fracture toughness versus yield strength, and you can see that these very high strength steels have a fracture toughness in the presence of hydrogen that is below 10 megapascals per square meter, so almost as brittle as a ceramic. So this is quite important because it's basically telling us two things. The first one is that hydrogen is compromising decades of metallurgical research. So we have developed high performance materials, but we cannot use them. And the second one is that by using these modern high strength steels, we're very significantly widening the range of environments where hydrogen is problematic. very little hydrogen content is sufficient to trigger hydrogen step failures in many applications and sectors where we never heard about this problem before. So hydrogen embrittlement has traditionally been a problem related to offshore structures, where we have very aggressive environments. But now we want to use these modern high-strength steels because they're very cost-effective. So we want to use them in our cars, in our buildings, in our bridges, in our railways. And this is triggering numerous hydrogen-assisted failure problems. You can see here in otherwise very benign environments. You can see here, this is a newspaper article from The Guardian. This is one of the main newspapers in the UK. And you can see that just the hydrogen coming from the humidity is enough to trigger hydrogen embrittlement problems in one of the most famous skyscrapers in London. And of course, this brings me back to my first motivation. If hydrogen can change by orders of magnitude the fracture toughness and particular growth rates in metals, how are we going to deploy this hydrogen energy infrastructure that we need to achieve net zero? And well, I guess the thing is that there's no way back. Politicians have already made a decision. I don't know if it's the case in Brazil, but in Europe, there's a big push now to establish green hydrogen as an alternative source of energy. You can see some newspaper articles here. So there's a lot of money going in that direction. And again, an impression that things need to happen very fast. There's a sense of urgency. You can see here, National Grid in the UK is hoping to have 5,000 kilometers of hydrogen transport pipelines in just 2 years. And that's going to be very challenging. In fact, we're already starting to see accidents, and the technology is not even there yet. This is in Norway. Very few countries have already started to establish the hydrogen technology, and we're already starting to see accidents there. And of course, what is missing here is a model. It would be fantastic to have a model that would allow us to predict these hydrogen step failures, because such a model will be a game changer. It will allow us to map safe regimes of operation. It will allow us to safely deploy a hydrogen energy infrastructure, and it will allow us to prevent those catastrophic failures. But developing a model for hydrogen step tracking is quite a long-standing scientific challenge. And I think there's two main reasons why we don't have a model for predicting these hydrogen failures. One is that the problem is it's quite a complicated problem that it crosses with multiple boundaries. So we do know a little bit of the physics, but not the whole picture. We know that hydrogen atoms coming from gas, electrolyte, or water vapor environments will enter the metal. They will migrate relatively fast through the crystal lattice, and they will accumulate in areas of high hydrostatic stress or high volumetric strains, where there's more space for the hydrogen to accumulate. But then hydrogen in this fractal procession interacts with the metal at multiple scales and in many ways, by changing the dislocation mobility, the bonding strength. So the physical picture is not clear yet. The second aspect to consider is that developing a model for predicting hydrogen step failures will require expertise across multiple disciplines: chemistry, condensed matter physics, mechanics, material science. So it's quite a complicated problem. So I tried to adopt some kind of a multidisciplinary approach and try to develop a computational framework that would allow me to predict these hydrogen step failures. And to me, the key to prediction is that you need to be mechanistic. You need to be able to resolve the physical processes that are governing all the stages involved in hydrogen embrittlement. From the uptake of hydrogen, the ingress of hydrogen into the metal, to the transport of hydrogen through the crystal lattice, to the embrittlement process itself. So the accumulation of hydrogen in critical interfaces and the nucleation and growth of cracks as a result of that. So let me tell you a little bit of how I came up with this model, but I think you probably get a clue at this stage that this is quite a beautiful problem because it is fundamentally very challenging. Many things are happening in there. It's very multidisciplinary. And at the same time, as I motivated before, it has very strong implications for engineering practice. So it's a very rewarding problem to work on as a scientist and engineer. So let me explain to you what we did. So the first thing is dealing with the hydrogen uptake. So there we had to propose new models that were able to capture, quantify the absorption of hydrogen into the metal as a function of the environment. There's two typical scenarios: gaseous systems and aqueous electrolyte systems. The gaseous systems are easier, and under certain conditions, you can find an expression that relates the hydrogen pressure or fugacity to the hydrogen concentration at the metal surface. The aqueous electrolyte system is much more complicated because you need to resolve all the surface reactions happening in the surface of the metal, and then you also need to solve the electrochemistry of the electrolyte, which can be very different inside of a pit or a crack relative to the bump. But we do know what are the physics, the equations that govern the hydrogen evolution reaction and the electrochemistry of electrolytes, so we can formulate a theory, and then we can implement that theory into a finite element code. So you can see here that This means that the kind of theory that we can come up with means that we're solving the Nernst-Planck equations for as many ionic species as needed in the electrolyte domain, and then you're solving the Volmer-Hurwitz Tafel and absorption reactions in the surface of the metal. And this is in addition to the other, well, these are the surface reactions, by the way. I'm not going to get into details, but the key point is that the model is physically based in that it doesn't require any prior assumptions. So one is the environment. You just rely on reaction rates that depend on the material and that you can measure in the lab. You can see that the pH and the overpotential come into play here. So the model is fully predictive in that sense. And at the end, you end up solving for as many, all of these are degrees of freedom in your finite element model. So you solve for as many ionic species as needed in the electrolyte, for the surface coverage in the interface. And then in the metal domain, you solve for the displacement and the lattice height concentration, among other things. So you end up easily with, I don't know, 10, 15 degrees of freedom per node. And this, of course, solving this 10 years ago was unthinkable, but I think computers have gone quite a long way since then. And we have also developed in my group new computational procedures that can significantly accelerate these calculations. And this is the kind of representative results that you get. So for a given environment, applied potential, you'll get a distribution of any relevant quantity in the electrolyte, in this case the pH, but it could be also the potential or any concentration of ionic species. And then in the metal, you can predict the absorption of hydrogen as a function of time. And you can predict this as a function of the material, the environment, the fluid velocity, the loading conditions, any scenario that you can think of. And once you know how much hydrogen is coming into the metal, then you can predict the transport of hydrogen within the metal itself to predict the distribution of hydrogen within your structural component. And one simple way of doing that is by using this extended version of Fick's law, whereby hydrogen is driven by gradients of concentration and also by gradients of hydrostatic stress. And this coupling with the mechanics is quite important in my opinion, because if you take, for example, the steady state solution of this equation, you end up with something like this. So you have a hydrostatic stress term inside of an exponential. So what this obviously means is that whenever you have a stress concentrator like a crack, your concentration of hydrogen is going to be much, much higher. So this is a key element that you don't want to miss in your model. Another important aspect of it is that hydrogen not only travels freely through the crystal lattice, it's also trapped at microstructural features like grain boundaries, carbides, or dislocations. So those microstructural defects will sequester the hydrogen away from the crystal lattice. So we have developed more sophisticated models based on Oriani or McNabb-Forster, where we can account for this distribution of hydrogen within the microstructure. We can predict where exactly the hydrogen lies. And once you know where the hydrogen lies within your material, then you can predict the fracture process, the brittlement itself. And for that, we have used those spatial models that I showed you before, which I think are quite powerful and will allow us to predict hydrogen state failures, not only in the idealized conditions of I would say, academic laboratory experiments, but also in the complex conditions of engineering practice. And one thing that I should say now is that, of course, I didn't say before, but being able to, the model is computationally very powerful, but being able to be physically sound requires a suitable description of that phase field differential equation, right? You need to be able, you need to make sure that those fancy colors that I showed you before represent some physics. And the good thing is that phase field in the concept of fractal mechanics provides a computational platform for Griffith's energy balance. So those of you that have studied fractal mechanics will remember that Griffith, the father of the field, postulated that a crack will grow whenever the energy is stored in the solid was sufficiently large to overcome the energy required to create tuner surfaces. So the express this, I would say, balance of energy in a variational form. And if you're able to minimize this functional, then you're able to predict the evolution of cracks just as an interplay between the fracture energy and the stored energy in the solid. However, the challenge here is that you don't really know where your crack surface lies, so it's a bit complicated to solve this computation. And this is where the phase field comes to our rescue, because we can use the phase field as a marker, allowing us to decide which variable. It will go from 0 outside of the crack in intact material points to 1 inside of the fully cracked material points, and it will degrade the status of the solid accordingly. And you can see here that it's kind of a non-local damage model because it has a length scale, there's a gradient, and therefore a length scale, which means that your results will be mesh insensitive, so mesh independent. And you can get a good overview by looking here at the So here is the balance of the density and the fracture energy, the material property that measures the resistance of the material to fracture. And just by solving this additional differential equation, you can capture very complicated cracking phenomena on the original finite element mesh and without any convergence problems. So all the results are based on Baker-Euler. Other examples here from the literature, some from our groups and from other groups, showing how these methods allow you to capture very complex cracking phenomena and allow you to do with experiments. So we have a lot of fun in the past 5 years working in this area. We have tried to contribute to the community, proposing new monolithic solution schemes, new formulations for functionally integrated materials, shear memory alloys, and other materials. But of course, we have not been the only ones working here. This has been really a revolution in fracture mechanics, and some people in this room, like Fernando, have actually contributed to this area much before I did, with new formulations for fracture and elastoplastic solids, and also for dilute species. So basically, I thought if I can extend the success of phase field to hydrogen and brittle, that would allow me to capture this completely field problem, so you solve the deformation. So then the transport of hydrogen, you need to, and the key coupling between these ones is the coupling between the hydrogen and the damage. Resistance of metals, so we need to hydrogen energy. But the key question is how to do this quantitatively. And I didn't want to present a model that required a lot of experimental calibration, so I needed to come up with a mechanistic degradation function that required no fitting parameters whatsoever. And I was able to resolve the physics of the problem. But before into this, let me say that the good news is that you can define this degradation function based on experiments. You can do experiments in multiple hydrogen crustaceans and measure fracture toughness. And some of our industrial partners are doing that. Or you can also come up with any mechanistic degradation law that you're thinking of. In fact, some other groups have taken on our framework and extended in other directions, making this degradation function depending on other micromechanical or macromechanical. But let me tell you a little bit of how I came up with what I think is the right hydrogen degradation function. And to do that, basically the key question that you need to answer is, how does hydrogen make metals brittle? How can it be that in the absence of hydrogen, a metal that fails in a very ductile manner, you can see here through micro-void cracking mechanisms, suddenly the moment you bring hydrogen into the picture, fails in a very brittle fashion, with cracks originating along the grain boundaries, as you can see there. And to me, the question to understand this, or the key to understand this problem, is to think of the problem across all physical scales. So if you think of it first from an atomistic perspective, what you learn from atomistic calculations is that hydrogen very significantly degrades the bonding strength between metal atoms. You can see here, these are DFT calculations for multiple grain boundaries in nickel. And you can see that if your grain boundary is full of hydrogen, a coverage of 1, then you get a 40% reduction in your surface energy or fracture energy. So hydrogen is going to make that grain boundary weaker. And then the question is, of course, how much hydrogen do we have in our grain boundary? Because if, it's very little hydrogen in my grain boundary, then there must be another mechanism taking place. So where are we in this x-axis? That's the next question. And the answer to that comes from the combination of trapping thermodynamics and experiments. We can use Oriani's equilibrium and we can measure binding energies in our lab. And there we can plot the trap occupancy as a function of the hydrogen concentration in the lattice and the trap binding energy. And this is a parameter that we can measure in the lab. And we know from our lab experiments that grain boundaries are quite strong traps. So they have binding energy of minus 40 kilojoules per mole. So if I go here, I can see that my trap is effectively full if I have as little as 1 part per million of hydrogen. So in other words, it is very energetically favorable for the hydrogen to accumulate in grain boundaries. And I know from the atomistics that this is going to make my grain boundaries much weaker. And then the next question is, okay, is it a 30 to 40% reduction in fracture energy or grain boundary strength sufficient to trigger a shift in failure mode from ductile to brittle? And in my opinion, the answer to that comes if you resolve the critical stresses of the problem over the critical distance, then, and for that, I'm not going to get into details, but for that, we use strain gradient plasticity theories because we know from experiments that the critical distance is of a few microns ahead of the crack tip. So you need to resolve the dislocation hardening mechanisms that govern crack tip behavior. But the key thing is that if you resolve the stresses ahead of the crack tip over the critical distance, what you see is that in the absence of hydrogen, your stresses are not high enough, so you don't reach that cleavage strength or grain boundary strength. But the moment you bring hydrogen into the picture, you get this 30 to 40% reduction in cleavage strength or in grain boundary strength. So we need to be able to capture how, as the crack propagates, So we need to be able to capture not only how the crack propagates, but also how the environment follows. Imagine you have a pipeline in the middle of the sea or pressure vessel with hydrogen gas. The moment the crack propagates, the seawater of the gas is going to follow immediately the crack. So we need to capture that. And you can do that easily through multiple ways in the model. The way we choose to do it is through a penalty approach. You can see here how as the crack propagates, the hydrogen concentration from the environment quickly follows. So let me show you some representative results with this framework. So what I'm showing here is what we call R curves, crack growth resistant curves. So this is a measure of the crack tip's loading conditions, and this is the crack extension. And we see what we expect from experiments, that as you increase the hydrogen concentration, you lower your fracture resistance. Here you see results for different loading rates. And again, we see another effect that we see in experiments. If you load very slowly your sample, you allow for more time for the hydrogen to accumulate in the fracture region, and therefore you lower your fracture resistance. But we can also provide quantitative agreement with experiments. Here you see experiments in the pre-charged steel bars. You can see these are measures for notch tensile strength versus hydrogen concentration. And you can see that the model agrees very well with the experiment, those signals that we see there. And these are a set of more interesting experiments. So this was done at Sintef in Norway. And what they did was they immersed notch Doppler stainless steel samples in the seawater bath. They subjected them to a constant load, each of them at a different load, and they measure the failure times. And as you can see, what they were hoping is that one of them will remain without failing for quite a long time, but all of them fail relatively early, simple type experiments in terms of engineering time skills. But what we can do with our model here is not only reproduce the experiments, but also run virtual experiments over very long time scales so as to determine what is the critical load below which we will not see anything. And essentially, we can do anything we want. We can simulate standardized lab experiments in our computers, but we can also deliver predictions for kind of the large scale engineering practice, so we can handle large scale 3D problems relevant to technologically relevant large scale 3D problems, as you can see here. And more excitingly, we can also couple this with inspection, creating sort of a digital twin of critical infrastructure. So what you see here is a 12-kilometer pipeline characterized by DB, and all these red dots here are pits, so they are defects originating from pit corrosion. So we decided to model a critical section of 3 meters that contain more than 100 of those defects, and then we can subject our pipeline to in-service conditions in the computer, and we can see how those defects are growing, how they merge, and how they stay over time. You can see here at the top, they started to merge, they start to coalesce into other defects, and then eventually to get the failure of the battery. So I think the takeaway is that at the end you have a tool, or we finally have a tool that allows us to predict hydrogen-assisted failures as a function of material, loading conditions, and environment. And this tool is mechanistic, that is in theory dependent only on nominal material properties, so physical parameters of the measure independently in a lab, but at the same time is able to deal with the large scales and complex conditions that are relevant to the methods. And we have recently extended this to fatigue, so you can have a fatigue degradation function, and then you can see here that you can predict virtual SN curves for with and without hydrogen, showing a bit of experiments. And we can also predict as an output of the model Paris law behavior, so we can predict what is the influence of hydrogen on the Paris law coefficients, and deliver virtual SN curves for any arbitrary choice job, example you see here, and environment, you see here very much sample. And these are cycle by cycle calculations, which are computationally heavy, but at the same time very powerful because they allow us to predict fatigue damage for any arbitrary load. Okay, so that takes me to the second part of my talk, lithium-ion battery degradation. The first one was the longest one, as you say, don't worry too much. Regarding batteries, this one needs no motivation, I think. All of you probably now have with yourselves a device like phone or a laptop that contains a lithium-ion battery. So I guess the key question for us is that we want our batteries to last longer. We don't want to change more than 2 years. We want the battery of our laptop to last for transatlantic flights. We want our electric powers to be able to go over hundreds of miles and so on and so forth. So there's a need to improve the durability and the performance of lithium-ion batteries. And I suspect most of you know how lithium-ion batteries work. So essentially, you have every time you charge the battery, you have lithium ions that go from the cathode, from these particles in the cathode, to these particles in the anode. And every time you discharge the battery, you have the lithium ions doing the opposite, going from these particles in the anode to these particles. And that lithiation of those particles, that exchange of those lithium ions inside of those particles causes some deformation within those particles. And that continuous cycling, charging and discharge of the particle, that continuous lithiation cycling of those particles, the swelling and shrinking of those particles causes the accumulation of cracks. And this is arguably the main degradation mechanism for lithium-ion batteries. So the reason why your phone needs to be charged every night is those cracks that are appearing in those electron particles as a result of discharge and discharge, this swelling and shrinking of the particles. So we try to use those models that I presented before, these kind of multi-physics based fracture models, to predict under what conditions we will see those cracks and to try to map safe regimes of operation of those lithium-ion batteries. And yeah, you can see here. So the idea is quite simple and quite similar to the previous model. So the equations are almost the same. You can see that we have again a three-field problem. In this case, we're modeling lithium diffusion instead of hydrogen. There's two main differences. The first one is that it doesn't seem that the lithium changes a lot in fact. And the second one is that we have these chemical strings that also exist in hydrogen, but they are very small, so we normally neglect them. But these are particularly significant in lithium, because the parcel molar volume is quite high. And in fact, these chemical strains caused by difference in concentration of lithium, the swelling and shrinking of the particles, is in fact what leads to those cracking process. We don't have any other mechanical load, it's just the lithiation process. So then we will, some people have used bulk magnetic accuracy, for example. They have used phasing models to simulate the failure of electron particles, but they did that only over 1/2 cycle. But of course, this is a cyclic process. So what we did is to add this fatigue degradation function and simulate the failure of these particles over hundreds of cycles. And not only looking at idealized particles, but also looking at realistic particles. And so we conducted cyclic loading over hundreds of cycles, and effectively you can see some representative results here. You can see the propagation of cracks in both idealized and realistic particles. And then we can use this virtual platform to map safe regimes of operations. We can, for example, change the charging rate, C rate, and determine what is the threshold below which we will not see crackings appearing in those particles. And we can also change, for example, the particle radius and determine what is the smallest particle that will give you this, or the largest particle that will give you the cracking problems for those loading conditions. So this is quite useful in terms of mapping safe regimes of operation and determining what is the right use of those batteries. But we've also taken this one step forward. So this is together with the colleagues at UCL. They have very advanced imaging facilities there. So they're able to characterize the full electrode. So not looking anymore at one particle, but looking at the full electrode. And this allows us to look at the secondary phases, so not only at the particles, but also at the binder, at the separator, and also looking at the heterogeneity of the problem. For example, you have a function with the electrode with particles of different size. We can play with the thickness of the electrode. So you take it one scale more. And computers are today, I think, sufficient to the day. So again, we couple this with this imaging facility, so we can do X-ray scans of those electrodes. But then we do the segmentation, so we can determine the different phases, the core, the carbon binder, the particle, and then we do our final derivative analysis. And we do this in 3D and encompassing dozens of particles. And these are some representative results. We can see that what is the distribution of lithium. We can see what is the distribution of cracks, where are cracks appearing. And we see a very heterogeneous electrochemical response. So we can see that first, the thickness of the electrode plays a big role, but we can also see that we may want to look for solutions that do not involve homogeneous distribution of particles. You can get very different responses within the electrode. And we have also taken this one step forward and simulated the microstructural fracture of those particles. Because often those particles fail due to grain boundary cracking. So we can particularize those Bayesian models that I showed you before, such that cracking only originates on the grain boundaries. And again, using these fantastic imaging facilities that they have at UCL, we can incorporate those multiple cracks into our problem, and then we can again do the similar process and determine what is the interest, for example, of using single crystal particles versus polycrystal particles. And this is something that the industry is now heavily considering, using single crystals to improve the battery performance. And this is the last item I will discuss in regards to batteries. This is quite exciting because this is the next kind of big disruption in battery technology. So the next big step will be to use what they call solid-state batteries. And the idea is to replace that liquid electrolyte. So that electrolyte I showed you before typically have these particles within a liquid electrolyte. And this is a problem because, you know, particles are flammable, batteries are flammable, so that's why we cannot carry a lot of batteries in a plane. We need to put it in safe storage, and that's why you see also some explosions of electrical bikes and so on and so forth. So the idea would be to improve safety by having a solid electrolyte, so replace the liquid electrolyte by a solid electrolyte. And also you can increase capacity by an order of magnitude, because then you can use lithium metal as an anode, which becomes stable with the solid electrolytes. It's not stable with those aqueous electrolytes. So you can increase capacity by an order of magnitude, and you can remove all the safety concerns related to batteries. So it's really the next big breakthrough in battery technology. There's a lot of effort going into this direction, commercializing these solid-state batteries. But the biggest problem is that the reason why we don't have commercial solid-state batteries yet is because we have this mechanical instabilities happening at the interface between the lithium metal and the electrolyte. You can see here we have cracks, we have wetting here, and the biggest problem is these dendrites. So these are needle-like structures of lithium that will start growing at the interface between the anode and the electrolyte, and they will grow all the way into the cathode, and they will cause the short circuit of the battery. So we need to be able to understand these mechanics problems in order to deploy or to achieve this big breakthrough in battery technology. So let me tell you a little bit of how we did that. There's a lot of, the community is basically divided into two lines of thought. Some people are trying to figure out what they can do to prevent those dendrites from growing. For example, putting very stiff ceramics as electrolytes and hoping that it will arrest those cracks, those dendrites. The other part of the community, which is now growing, is thinking that it is impossible, it seems impossible to stop those dendrites from growing. So if we can understand under which conditions those dendrites will form, then we can also find a solution for this battery problem. So I've been working on it for quite a while now, and this is what you see typically when you have the solid-state batteries. So this is some very nice SCM images from the group in Oxford. So first you have you start at the very beginning with a pristine, almost perfect anode electrolyte interface, but every time you discharge the battery, you remove lithium, and therefore you create these voids here. You can see those voids. And every time you charge the battery, you plate lithium, you deposit lithium, and therefore those voids shrink, and sometimes they become occluded from the interface, they separate themselves from the interface. And being able to capture the evolution of these voids is critical, because in the edges of those voids, you get what we call current hotspots. So regions, localized regions where the current is very high, and because the current is very high, then during plating, that's where you deposit the lithium and you get the dendrites. So if you can eliminate these hotspots, if you can eliminate the hotspots, we eliminate the dendrites. And in order to eliminate the hotspots, we need to understand how those hotspots are generated in the voiding system. So we need to simulate how those bodies grow under which conditions and so on. And this is quite an interesting, I would say, multi-physics problem that again has a complex interface involved. In this case, the interface is not a crack, are those bodies the lithium metal, but this is what we try to simulate. So again, a suitable problem for phase field multi-physics model. And this is what we try to do. So the model that we have to develop a model from scratch, and the ingredients that we introduced in our model, which we thought these were the most important ones, was first you need to capture those interface reactions. So every time you have plating or stripping, you have basically lithium atoms being either removed from the metal or being deposited in the metal. So that you need to capture. We capture that through boundary condition. You also need to capture vacancy lithium diffusion, so solid state diffusion of lithium, lithium atoms moving to the anode. This leads to some mechanical issues. So you have these chemical strains that we discussed before. You also need to have the generation, you need to capture the generation and growth of those bodies. And this is basically vacancy equation or inundation. So you need to describe the equations, the formation and the evolution of those bodies. And for that, we use the phase field. And then you have a lot of mechanics in there. In fact, the mechanics here is creep and viscoplasticity. Because the main hypothesis in the battery community is that they will be able to solve all these void issues if they apply a stack pressure to the battery. They say, we're going to apply a pressure, and therefore we will kind of shrink those voids, we'll kill those voids. So we need to be able to capture this constant stack pressure and how the material is redistributed to creep and viscoplasticity. So lithium is quite a soft viscous material. And so this is kind of, you won't see maybe the equations here, but this is kind of the model that we have. So we solve an electromechanical problem. We have an equation for the lithium vacancy diffusion, we have an equation for the electrical field, we have a phase field equation that describes the evolution of those voids, and we have also all the creep and viscoplasticity. And these are the kind of results that we get. This is for stripping. You see on the left, this is a single void, this is the phase field, and this is the current. And you can see that we see what we predict in the experiments. So the void is growing, actually it's growing with a similar pattern to what we saw in those SEM images before. And you can see that naturally the model is able to capture how the current localizes in those edges of the void. So we can measure those current hotspots and determine when we reach critical value. And this is what you see when you get plating. Again, you see how the void starts shrinking and how eventually it separates itself from the interface. So it's exactly what we're seeing qualitatively, at least on the experiments. And again, we can see how those hotspots eventually disappear with the plating cycle. So we replicate the charts. And we can do this, of course, for much more, I would say, technologically relevant conditions where we have multiple charge and discharge cycles, where we have multiple voids that interact with each other. We're doing this at the same time as we apply pressure, so we're able to capture how those voids eventually shrink and at which pressure we will make those voids disappear. So effectively, again, the takeaway is that we have a virtual platform that allows us to map what are safe regimes of operation, what are the regimes that will enable a breakthrough in this solid state battery technology. We can predict this boiling and hotspot phenomena as a function of the pressure, of the material, of the geometry of the cell, of the mold, the material of the electrolyte and the anode, and so on. And one last thing about the solid state batteries, we have also been working on what we call anode-free batteries. It's one where you don't start with any lithium and need to deposit the lithium in the first plating cycle. And this is something that we have done with Aula in Georgia Tech, and they did a very nice experimental studies, and we were hypothesizing the problem was that the initial plating was not uniform, and this led to the boiling and the creation of hotspots, and we were able to show that with a final. Okay, so that takes me to the very end of my talk. This is the corrosion part. And again, this is another area that needs no motivation. Corrosion is, I would say, one of the grand challenges of science and engineering. It's been there for quite a while, and we still don't fully understand it, or we're not fully able to prevent it, basically. I mean, it has a massive cost. All in the UK, it has a cost of £46 billion per year in the UK, so it's really a massive cost to society. It is often labeled as the biggest threat to sustainability and durability of materials. It can result in catastrophic failures. And again, it's exciting to work on it because it has a long-standing scientific and engineering challenge, and one that has resisted our computational efforts. So if you go to the corrosion conference, you will find that 90% of the works are experimental, and the other 10% will be atomistics. And when I talk to my corrosion colleagues, they will tell me, yeah, this is a too complicated problem to deal with. It's just too many things happening at the same time. you have this complex interface involving, we're really not there yet. So it's very complicated to develop. But I think that we finally have enough computer muscle and enough understanding to leverage those decades of very good experimental correlation science research and build and develop predictive models. And one of the reasons, there's multiple reasons why this problem is quite complicated to model and we haven't been able to model so far. The first one is that, I said two things. One is that you have a complex morphology, and the second one is that there's a lot of things happening and they're always going to happen. So for example, you can see here, this is corrosion fatigue of offshore winter banks. And this is the service life of offshore winter banks, which is only estimated to be 25 years based on very empirical design rules. So there's a very strong need now to develop more mechanistic models to decide on whether to extend the lifetime of offshore wind turbines, because the oldest ones are starting to reach the 25-year-old cycle. But it's quite complicated. As you see, first you get peaks and nuclei at the interface between the aqueous electrolyte, the seawater, and the metal. Those peaks grow, driven by local chemistry and mechanics, and eventually you get this kind of peak to crack transition event and the propagation of fatigue cracks. So the key thing is that, first of all, you need to be able to capture a very complex morphology, so that the corrosion part, because it has a very fine shape, you need to be able to capture how it evolves. And the second of all is that it's very strongly coupled problem. So if you want to resolve the physics of this problem, not only do you need to couple the chemistry, the mechanics, and so on, but you need to couple all of these elements, because I'm with the interface morphology, because the shape of those peaks is going to be determined by the local chemistry and mechanics, but the local chemistry and mechanics are themselves dependent on the shape of those peaks. So the pH will change drastically instead of a peak. As you know, a peak is a stress concentrator, so it becomes very sharp, the stress are going to be higher. So everything is very strong fact. But I think, again, this seems like a very suitable problem to tackle this interface modeling and multiphysics modeling. So we decided to do that. We decided, okay, let's go and use the phase flow now to describe the interface between seawater and the metal. And I won't get into the details for the sake of time, but these phase models are more similar to those used in microstructural evolution. So you have essentially the KKS model. So you have basically two equations, one that describes the short range interaction, so the corrosion process itself, the dissolution of material, and another one that describes the concentration, the diffusion of metal ions away from the corrosion. And again, I'm not going to get into the details for the sake of time, but essentially your model has two key parameters, the mobility coefficient of the phase flow and this diffusion coefficient of the metal ions, and both we can relate to physics. So as you can see here that it works, you can see here a peaking, for example, the growth of a peak, and here you can see more of this kind of a stress corrosion cracking phenomena, which is kind of peak to crack transition as we. Here we're considering different conditions. There's no applied load here, there's the oscillation here, so we can naturally capture these different scenarios that we see corrosion. And this is just a classic paradigmatic example to show you how the model can go from activation control corrosion to diffusion control corrosion, which are the two main regimes of corrosion. So this is effectively a 1D problem. You have corrosion of this metal layer, metal wire, and it's a 1D problem because you're protecting this, so it basically corrodes uniformly in this direction. And there's analytical solutions for this problem in the diffusion control corrosion regime. And this is what you see with the model. You see effectively how the corrosion front evolves, and you see here the distribution of metal ions away from that corrosion front. And you can compare the model predictions with analytical solution and their diffusion control conditions. And we can also see that the model is naturally able to capture how we go from activation control corrosion, so this kind of linear behavior, to diffusion control corrosion when corrosion rates are so high that diffusion is the limiting step. And in diffusion control corrosion regime, of course, the results are dependent on the diffusion. But anyway, we can predict not only 1D, of course, but also 2D cases compared with other calculations. And we have also introduced two mechanical elements that I think are important. The first one is the fact that we know that mechanical fields enhance corrosion kinetics. We know this is the work by Goodman. This is the corrosion rate, and you can see that it depends on the plastic strains and the hydrostatic stress. So we can incorporate that into our model because you can make this phase field mobility coefficient that you can relate quantitatively with the corrosion current density, and you can make it dependent on these mechanical fields. And we have shown to validate this problem with this kind of sealing test under different loading conditions. And you can see here the comparison with experiments, so a very good agreement in terms of the length of the corrosion region, but also we can get the right morphology. So these two images are on the right in the same scale. We choose to model only one peak, but we could have modeled more, and you can see that we get a very good agreement in terms of the shape of the peak as well. And the last thing that I want to say is that we have also extended this to account for this film rupture reconciliation kinetics. So normally, for example, in stainless steel, you will create a film that will protect the metal from corroding, but we get localized corrosion and peaking and stress corrosion cracking because that film ruptures eventually. So effectively, your corrosion process is a competition between the grafted strain rates and the repassivation rates. So we can capture that. We can capture how the film eventually ruptures and then repassivates, again by defining suitably the mobility condition. And you can see here this example of the different environments. We have faster or slower repassivation, and we see the trends with respect to different experiments. And because we're dealing with phasing, again, we can deal with any complicated condition and multiple things that eventually interact and so on. And we can do this in 2D, we can do this in 3D, and so on and so forth. And I'm quite excited about the whole thing because I think that this platform can very easily couple with other equations. So it is true what my experimental friends in corrosion science say. Lots of things happen in corrosion. It's a very complicated problem. But we understand those things thanks to that good experimental effort. So we can incorporate those things, we can incorporate those equations to our model. So we can capture the role of the electrochemistry, we can couple that with those hydrogen problems before. Occasionally we have hydrogen uptake into the metal as a result of the corrosion process. We can capture also intergranular corrosion here. You can see here the role of the microstructure. So you can see here, for example, that we know that the microstructure plays a role from a mechanical point of view. You have this mechanical anisotropy, but also we know that corrosion can be anisotropy. So corrosion rates are sensitive to the crystallographic anisotropy. So we can extend the model and define a gradient orientation dependent corrosion potential, and we can then capture the effect of the microstructure. So you can see here, this is a microstructure insensitive calculation, but we can have any microstructure that we wish, and we can see what is the role of the microstructure in changing the corrosion process. And we can also do more complicated things. For example, you can have secondary phases, and the corrosion will not deal with those insoluble phases. So you can have very complicated microstructures into your model, and you can also capture the role of the chemistry. So here we can solve for as many reactions and ionic species as we want, similar to what we did in the beginning with hydrogen, and we can capture the role of the solvent concentration, of the pipe potential, and so on and so forth. So as the peaks and the cracks propagate, you can capture how the environment is naturally evolving with the result of this corrosion process. So a lot of things are happening, but all of those things can be simulated with this framework, provided your computer is large enough. And we have also very recently extended this to deal with biocorrosion. So there's a lot of emphasis in using magnesium for implants, because magnesium is biodegradable. So we will naturally degrade into the body, and therefore, whenever a kid breaks its bones, you don't need to do a second surgery to remove the implant. You can just allow for the magnesium to degrade. The problem is that the magnesium is degrading too fast, so there's not enough time for the bone to heal. So there's a lot of effort in the scientific community in trying to alloy, perhaps to try and have the solutions like alloying that magnesium or coming up with composites. But they don't have a nice model to look at this. So this allows us to predict that kind of biocorrosion. And this is very good because we can validate our model with in vitro conditions, so things that people can test in the lab, and then we can go into in vivo conditions, which are different and have different environments, but those come naturally in the model. So yeah, thanks a lot for your patience. I'll just finish with a few concluding remarks. First, I would say that to me, the discovery of phasing has been fantastic. I consider myself a computational fracture mechanics person, and I've tried absolutely every method out there: XM, physical modeling, remeshing. I went to the conference, I saw people presenting nice videos. I came home, I reproduced the video, then I changed something, and then nothing worked. I did the same with Facebook, but everything worked, everything was very robust, very smooth. So I really committed myself to their cause. So I like to talk about it because it has been a game changer for me. And it has only been a game changer not only in fracture mechanics, but any interfacial problem. So we have shown that it can be a revolution in corrosion, and I think that it will be a revolution similar to what we're seeing in fracture. But we have also shown that it can be used, for example, to predict the evolution of voids in solid-state matters. And I think that this coupling with phasing and multi-physics problems is very powerful because it allows us to physically resolve the underlying physics of the problem. So we don't need to make any strong assumptions. We just say, we know what are the physical mechanisms happens, we know what are the differential equations of the mechanisms, let's bring them all together. And at the same time, we're also able to deal with the large scale and complex conditions of engineering practice. And I think we can make a difference in many areas that are relevant to the energy transition, like, for example, the failure of metals exposed to hydrogen. And our industrial partners are using those models that I showed you before to predict, to deploy a hydrogen energy infrastructure, for example, to design the pressure vessels for hydrogen storage, or to determine under which conditions we can transport hydrogen in the gas pipeline network. Also, in battery materials, we are using these methods to develop a kind of virtual platform where we can test different ideas on how to make our batteries more durable, more high performance, and we can also at the same time map safe regimes of operation where we don't have these mechanical problems that are degrading our current batteries. And finally, the corrosion of metals in the industrial environment, which is kind of a long-standing challenge, but I'm convinced that we have finally the tool to prevent when these things will happen. And also to try new strategies, new protection strategies, new materials, new microstructures, and see what happens in those moments. And just to conclude, I will emphasize that I share all my codes. We normally use Aula for console, but also Phoenix or our own codes. So all the codes that are, all the results that I showed you before, you can download my codes from my website, and then you can reproduce the results at home. And if you have any problems, of course, feel free to send me an email. I'm happy to help you. And of course, many thanks to the sponsors and to all of you for your patience. Thanks a lot.
And the track starts at the grade box, right? So how the track propagates when the dolphins are propagated by inside the track, like after the game.
Yeah, thank you. Good question. So it's very much dependent on the material and environment as well, and the conditions. So we have seen, you can see all circumstances. In general, it is quite common for cracks to propagate on the grain boundaries and for to have intergranular cracking, so the crack to grow through the grain boundary. So that was the case, for example, of nickel alloys. I was showing a picture of nickel before. So the examples that I put were mostly relevant to this situation. And we have, I didn't show for the sake of time, but we have also had this kind of microstructural models where we look at competition between transgranular cracking and intergranular cracking and how it changes from one to the other. I would say in many cases, you can start in austenite prior grain boundaries or grain boundaries in nickel. So in many cases, it's an intergranular cracking mechanism, but not always. In some cases, particularly some ferritic steels, austenitic steels, sometimes you get transgranular cracking and a mixture of kind of cracking features and cleavage features and some background features. Yeah. Thank you.
I got a question about the last discussion of the conversation about the road. Do you have the problem of stability? That the position of the people is something like they are confusing one those the name of people.
When you have multiple bits?
Yes, everything is, if you can isolate only one bit and analyze only one, forgetting the name of the, I am the one that they are for
Yes, no, that's a very good question. And I think if you want to model the realistic scenario, you need to account for this interplay between the multiple bits. And it is true that at the end, often it's a little bit similar to what you think of when you have multiple cracks. So one of them becomes dominant and kind of relaxes the stresses around it. So you do need to account for the competition, but there's a point after which one peak becomes dominant, relaxes a little bit the other ones, and that's the one that goes on to transition into a crack. But ideally, if you want to reproduce what is happening in reality, there is at the beginning, particularly for the nucleation, this interplay between multiple peaks. I think peaking in general, the nucleation peaks at the very beginning is quite complicated. It's a very stochastic process. We're working on it, but it's the most complicated part. It's a bit easier when you have already some expectation of what the pit looks like, what is the dominant pit, and then you start your calculation from there and look at how the pit will grow, what it will transition into a crack.
something like
Yeah, what I've seen people doing and what we're doing a little bit now is kind of a stochastic analysis, probabilistic analysis. We have multiple microstructures, and because sometimes the pits originate into some magnetite that is left from wells, so you have this complicated condition where you have multiple materials. So it's not impossible. And in principle, with all the physics, we can come up with a differential equation. We can use it in the computer, but sometimes it's so sensitive to these details that we need to run some sort of a statistical analysis. Thank you.
mentioned that it's been 5 months for hydrogen. So much to ask how the industry is dealing with this problem. And if they are trying to do that or what kind of research they are trying. I know there's a lot of answer to the problem, but we are exposed.
No, it's an interesting question. So some people sometimes see what I present and they say, well, having is so bad for metal that I mean, we should abandon this idea, right? I think now, at least in Europe, where they have committed to, they have very strong commitments in terms of net zero and zero emissions and so on. So they're planning to, in the UK, I think it's now 2040, reduce all emissions. So when people that know about economics, when they do this business case study, they figure out that they need everything. They cannot achieve those commitments without hydrogen. So maybe hydrogen will be the solution for all things, but some things like aviation or steel making, you cannot electrify those scenarios. You don't have a big battery for the battery. The size of the battery to do a transatlantic flight will be the size of the Earth. So it is simply impossible. So they recognize that hydrogen has to work. And then can you make hydrogen work? In principle, you can. So some materials are less susceptible than others. For example, austenitic steels, but they're very expensive. And in principle, if you keep your hydrogen levels low, you can use it. So the idea first with our model is, okay, can we map safe regimes of operation under which conditions you won't have hydrogen in between products? It is true that those conditions are small, and hydrogen requires high pressure because of the power energy density. So you need, ideally, the ideal scenario is one where you have these pipelines with very high hydrogen pressures, and 100 megapascals, 80 megapascals, something like this. And therefore, hydrogen becomes economically very competitive. Otherwise, you can make it work, but it's going to be very expensive because you can transport very little content of hydrogen in very expensive materials and so on. So the industry is hoping that they will be able to transport hydrogen at high pressures and purities, and that they will be able to do that in hydrogen in a natural gas pipeline network. So they don't have to build 50,000 kilometers of pipeline. They just take the pipelines that are being used for the natural gas and they put the hydrogen in there. That's the ideal case. What they are doing now is they're doing some tests, very large scale tests that are very expensive. So they have a hydrogen gas pipeline, they introduce hydrogen, they wait a little bit and see what happens. But this is a bit tricky because first pipelines can change quite a lot. These pipelines have been there for 30 years, some of them. So some of them have a lot of defects. The ones you are testing maybe are not the most representative ones. It could also be that, of course, this is a fatigue problem. So you cannot just do a test of a week and hope that this will give you the answer for 50 years of service. So this is where our models also come into play. So we are working with industry, for example, in testing under very long service times. What are the conditions in terms of hydrogen purity and pressure that are allowed in old pipelines and in new pipelines in different materials and so on and so forth. So I think there is a solution, and it seems that we have to take that solution, otherwise we cannot meet those kind of change requirements. But we will have to balance the economics with what is possible with hydrogen. And I suspect that if industry is pushing the limits, we will see a lot of hydrogen failures, and so that will keep me busy for some years. Thanks.
So, like, congratulations on your application. In here,
A little bit.
I'm part of the technology department, but also I work with the some simulation, like but I have some problems, some trouble like because I'm a part of analytical department. So then they do all of things like thinking very complex and microstructure scale. So how can you handle it with you have to simplify the problem, simplify the solution, and you are between two areas where you fight with each other. How can you
That's a very good question. Yeah, so I didn't show for the sake of time, but traditionally people interested in hydrogen did not care that much about the microstructure in the sense that in terms of hydrogen is their cracking. They are interested in the microstructure, the fact that it plays in diffusion and so on, but those things we measure in our lab. And the reason was that normally we were looking at hydrogen in very aggressive environments. So in those situations, you already have big defects. Okay, maybe I can just so in those situations, you already have, can you hear me? So in those situations, you have already big defects because maybe you have peaks already and so on.
So those defects are of a scale that is comparable to the microstructural scales, then the microstructure has to basically. So traditionally, it hasn't been that much of an issue, but now, when you're looking at the hydrogen energy, for example, they're looking at storing hydrogen in pressure ratios, they're looking at using very clean organic stainless steels, and there you don't have any big defects to start with. They try to remove the pollution, they work with great clean steels, and there, most of the service line is actually initiation of a crack, and there the microstructure plays in. So that makes it more complicated, to say. It's not impossible, again, maybe brings a bit more statistics at all, but we can, in principle, simulate the microstructure and usually methods to be able to handle this microstructure. But in principle, it is possible. It's a bit more complicated, but it's not impossible to show some microstructure calculations. It's not impossible to explain the microstructure and capture some of these more complicated effects that have in the past of the lower scales. But it is true that for many kind of large scale simulations, like for existing patterns, which already have effects, it's not a problem. For this other application, where we're dealing with very smooth and defect-free components, there the microstructure plays a bigger role, and it makes it more complicated, but again, not impossible because we can simulate without place of plasticity, without we can generate rates, we can go to DSD and formulate our microstructure. So in principle, it is not impossible, but it does make it more complicated.
Thank you.
Thank you. Thank you.